All right, so the last section that we'll take a look at is 8.5, part 4. So this will be section 5.6 in the book I've been using with you guys. So we're going to look at everything that we've pretty much done in 2D, and we'll do the same thing again in 3D. But since we already know how to do everything in 2D, the 3D is basically exactly the same way. It's very, very similar. So it's kind of a review of everything we did in 2D. So when we work in 3D, we now have 3 axes, X, Y, Z. And this particular arrangement that we use, it's called a right-handed coordinate system, because if your index finger is the x-axis and your middle finger points in the direction of the y-axis, your thumb will point in the direction of the z-axis. So all 3 axes are perpendicular to each other. If you did a left-handed coordinate system and you line up the x and the y like that, then what happens is the z's point in opposite directions. Right? So we always use what's called a right-handed coordinate system. Everything that we've basically done has been in this area here. That's the XY plane. So if you had your desk in front of you, think of your desk as the XY axis. X-axis is left and right, Y-axis is up and down. The Z-axis is coming off of your desk. And the positive direction of the Z-axis is up. And the negative direction would be going down. Okay. Any question on that? All right. So one of the first things we're going to look at, and this doesn't specifically involve vectors, this is just 2 points, is how we find the distance between 2 points. And we're going to do it in 3D. So in 2D, that is your distance formula. Everything I do today, I'll put up the 2D version of the formula first, and then we'll extend the formula to 3D. Okay, so distance formula in 2D, you find the difference between your x values, you square it. Distance between the y values, square it, add them up and take the square root. Now, the distance formula is really what formula? It's not its own formula. It's just a formula we already know by another name. Julia?
Like x2 minus xy and like y2 minus y1, or it would be for slope, right? So is that what it's
So we're not finding a ratio of them. We're adding them. If you had a ratio of them, that's slope. But no, we're not quite doing slope here. Yep. We're doing Pythagorean theorem. Okay. If you have 2 points and you do x2 minus x1, that's telling you the horizontal distance between the 2 points. That dotted line. If you do y2 minus y1, that's telling you vertically how far apart the 2 points are. Well, if you find that distance and square it, you find that other distance and square it, and then you add them up and take the square root, you're finding the hypotenuse of the triangle. And that's the distance between 2 points. So now, let's extend it to 3D. So in 2D, your coordinate would have an x and a y value. In 3D, your coordinate has an x, a y, and a z value. Anyone have a guess how we're going to extend the 2D formula to be a 3D formula? That's all every formula is today. It's just an extension of the 2D, like doing the same thing one more time. Yep?
Would you just add the z as well, like plus z2 minus z1
Right.
squared?
So it's everything that you did in 2D. Find the difference in the x's squared, the difference in the y squared. Now you're going to add the difference in the z's squared. And that is the distance formula in 3D. So no, that's not a vector formula. It's just how to find the distance between 2 points. Okay, so let's try an example of that. So the 2 points we have are -1, 3, 2, and 4, -2, 5. Okay, so what I like to use is write down everything first without numbers, and then we'll plug it all in. Distance equals. Something there squared, there, and there. Okay. What's going to go in my first set of parentheses? Yeah. So if we follow the pattern.
Before plus 1.
Yeah. So if we follow what they have up there, they're doing x2 minus x1. So that would be 4 minus -1. No. Okay. And how about in the second set of parentheses? Yep, Julia.
-2 minus 3.
-2 minus 3. And in the last set? Yeah.
5 minus 2.
5 minus 2. Okay, so we plug it all in. Now we just have to see what it comes up to. Okay, what's 4 minus -1? Yeah. 5, and then squared? 25. Okay, what's -2 minus 3? Of course.
-5.
And when you square it?
25.
25 again. And lastly, 5 minus 2, and square it. 9. So what is the distance between those 2 points? Square root of 59. Okay, if they would like a decimal, we can just type it in on the calculator and figure out the decimal. That's it. That's the distance between 2 points in 3D. Any questions on that? All right, so next thing. Let's look at vectors in 3D. So in 2D, that is how you write a vector. What does the A represent? That's the
Yeah.
Horizontal component. Yep. So A is the horizontal component, or you could say the x-axis component. Yep. And what's the B? The vertical component, or we call it the y-axis component. Yep. So A and B are the components. So now in 3D, we're going to extend that a little bit. A is still going to be the x-axis component, and I is, remember, a unit vector that points 1 unit to the right. If you want it to point to the left, we can do that. We just make the A negative. B, that's going to be my vertical, or well, it's going to be my y-axis component. And that's the y-axis component because it's being multiplied by the unit vector j, which is a unit vector that points 1 unit up. So in 2D, that's all we needed. We could stack i's and j's together to build any vector we wanted. So that would be like 3i plus 4j. But now what we might have is some i's, some j's, and then we might have it coming out from the board. So what do you think we're going to call the third component? Okay. And what is going to be in front of that? C. Yeah. So we're going to have C, which will be a number, And that's going to be multiplied by the unit vector k. So the unit vector I is 1 unit long on the x-axis, j is 1 unit long on the y, k is 1 unit long on the z. So now we could stack some k's together coming out from the board, and we could connect where we started to where we finish in 3D. Okay, so remember, A, B, and C, those are the components of the vector. If you don't want to write it in the unit vector form, you can also write it with the angle brackets, just like we did with 2D. Okay, I'm going to try to get away from saying horizontal and vertical components now, because if you think of like your desk in 3D, the vertical component is coming off of your desk. That's really the Z now. Okay, the X and the Y are flat on the desk. I would think of the X as the left and right, and the Y as the forward and back on the desk. And Z is up off the desk. Okay, what do we call a vector that has its initial point at the origin? One of the last things we did in 2D. Yep. It's what?
It's like a something.
Yep.
It's a position vector.
Position vector. So we use exactly the same thing in 3D. If you have a 3D vector that starts at the origin, it's still called a position vector, just like 2D. Okay, and we had that formula for finding a position vector in 2D. Okay, so anytime I write recall, you already have that. Okay, that we did first day of class. The only thing that you have to make sure you know if you're trying to find a position vector is where it starts and where it stops. And the formula is terminal minus initial. That's how you figure it out. And you have to do that for the x component and the y component. Okay. Now, in 3D, how are each of my points going to change? The initial point and the terminal point to make those 3D. Yep. We're going to have a z component. So we'll have an initial point and a terminal point. Each coordinate will have 3 numbers, an x, a y, and a z. And what do you think we'll do to find the position vector? How are we going to extend the 2D formula to be a 3D formula? Yep.
Adding z.
Can you explain to me how it would look?
You do comma z2 minus z1.
And what would you start with?
Oh, x2 minus x1,
Yep.
y2 minus y1,
Yep.
z. That, yeah, z's.
And then you'd have the z2 minus z1. Okay, so that's extending the position vector formula to 3D. It's the difference in the x's, comma, difference in the y's, comma, and the difference in the z's. And remember, when you find a position vector, you're finding a vector. So either put angle brackets around it, or you can put the I, the j, and the k. But you need to do one of them. We'll try both on this one. Okay, so here's our 2 points. We've got negative 1, 2, 3, and 4, 6, 2. And the directions are find the position vector. Okay, so how about Nick? What are going to be the first 2 numbers that I subtract to get the x-axis component.
4 minus -1.
4 minus -1. Yep. Luke, how about the next two numbers that I'll subtract to get the y-axis component?
2 and 6.
And how? So what would your calculation be?
It would be 6 minus 2.
6 minus 2. Yep. When you are finding a position vector, it has to be terminal minus initial. And what about to get the z-axis component?
2 minus 3.
2 minus 3. Okay, so we simplify that. If we want to write it in that notation, we get 5, 4, 1. Whoops. 5, 4, -1. And how would we write that in unit vector notation? Yep.
5i plus 4j plus, or minus 1k.
Yep. Okay, both answers are they're both fine. Just make sure you read the directions on the test when it asks for a certain format and use the format they ask for. Any question on finding a position vector in 3D? So the next thing we did, that ended the first day of notes. Position vector in 2D is where we stopped. The next day we looked at how to add, subtract, multiply, and scale vectors, all with formulas. Okay, no sketching. All right, so let's start with v plus w, but let me make that full screen so we can see it. Okay, if we wanted to add these two vectors up without using a picture, in 2D, you would take the x components, you'd add them. You'd take the y components, add them, and you'd be done. What are we going to have to do now to extend it to 3D? Right, we're going to have to add the z components. So to add together two vectors in 3D, take the x components, add them, the y components, add them, the z components, and add them. And same idea for subtracting. If you want to subtract two vectors in 3D, we're not going to take the second vector and flip it around and try to sketch three-dimensionally. We're just going to use the formula. Subtract the x's, the y's, and the z's. Okay, how about if I did something like this? What do we call this? Scalar
Multiplication.
Yeah, scalar multiplication or a scalar product. Yep. And when you scale a vector, what can happen to it? Yeah.
It can get bigger, get smaller, it can reverse its direction.
Right. Can get longer, shorter, or change direction. When we do it in 2D, I told you to think of it like a distributive property. Whatever your scalar is, you distribute that number to the x component and the y component. What else are we going to have to do now in 3D? Yep.
You have to apply to the z.
Yep. We're going to have to distribute it to the z component. So whatever number is in front of your vector, you're going to multiply that number out to each component. Okay, and the last formula we did in 2D was for that. And what does that symbol mean again when we put a vector with the bars around it?
Magnitude.
It means magnitude. Okay, now in 2D, can someone remind me what was the formula to find the magnitude of a vector in 2D? Yep.
X, the square root of x squared plus y squared.
So we had the square root of, we had the x squared plus the y squared. How are we going to make that last formula 3D? Nico?
Z squared.
We're going to add z squared. Yep. You basically can think of every problem we've done up until today as the z being a 0. It was never there. So it's not like you have to memorize 2 different versions of every formula. I would just always use the 3D one. And then if you only have a 2D point, then just ignore the z. Don't use it. Which is what we've been doing all week. All right, so here's 2 3-dimensional vectors in unit vector form, and they want us to add them, find the magnitude, and then it looks like, I think, a scalar. Okay, since they gave us the vectors in unit vector form, we'll give them the answer back in the same form. Start with I. What's going to be the number in front of I when we add those 2 vectors up? Yep. 5. Yep. So we got 5i. How about for j, our y-axis component? Yep.
Would it be negative j?
Negative j. And for k, what are we going to get for that one? Yep. 3k. So if you wanted to think, what would that look like if you were to build that vector? Like on your desk in front of you. So you're going 5 units right, 1, 2, 3, 4, 5. You're going 1 unit down, and then you're coming out 3 units off your desk. So that's what the vector would look like. Magnitude. Okay, and it's just the magnitude of v. You don't need w, just v. Okay, what's going to be my calculation to find the magnitude of v? Yeah.
It would be the square root of x1 squared. You know the numbers are like the, okay.
Yeah.
So it would be 2 squared, and then 3 squared, plus 2 squared, and then minus 2 squared.
And then minus 2 squared?
But yeah, that works out.
So were there any minuses in the formula that we wrote on the left?
Oh yeah, I got you. It'd be plus 9 to 2 squared.
Yeah. So it's always plus signs, and then if you have a minus, well, that might come from the number, but that's going to cancel out anyway when you square it. So what's that going to give us the square root of? Yep, 17. 4 plus 9 plus 4. And that's the square root of 17. Okay, any question on finding the magnitude of a vector in 3D? Okay, so we add, we did magnitude, let's do scalar. Okay, they want us to find 3w. 3w. So what would you get if you took w and tripled it? Works?
9i minus 12j plus 15k.
So remember, you think of that 3 as like a distributive property, and you're just multiplying it out to each component that you have. So 9i minus 12j plus 15k. Any question on scaling a vector in 3D? All right, so that pretty much summarized everything that we did in 2D on Tuesday. So now, what did we look at yesterday? Yeah. Angles, and what did we use to figure those out? Yeah.
The dot thing?
the
Dot product.
dot product.
Thank you.
Dot thing.
Okay. So now we're going to look at the dot product in 3D.
Dot.
I like that.
What would be the what's the dot product in 2D? Using those values up there. Yeah.
X1 and Y1, and then X2 and Y2. You'd only use those.
So what? So if somebody said, "What is the formula?" What would you tell them?
Give me a second.
What's the actual formula? Yeah.
X2 times X1 plus Y2 times Y1.
Yeah. So we're going to multiply the x's together, multiply the y's together, and then add them up. All right. So that was. There's your 2D formula. And what do you think is going to be on the end of that to make the dot product 3D? Yeah.
Plus, parentheses, Z1 times Z2.
Great. So everything we've done today is just extending the formula we already had for one more step. Multiply the x's, multiply the y's, and now you also multiply the z's, and then add those three products together. Yep. Okay, so let's find the dot product between the two vectors v and w. V is 2i minus 3j plus 6k. And w is 5i plus 3j minus k. Okay, Mia, what are the first two things I would multiply together to get the dot product? 2 times 5. Yep. So 2 times 5 plus, what would be the next two things I multiply together? Yep.
Negative 3
Negative
times 3.
3 times 3. Okay. And if that was 2D, we'd be done. But now in 3D, what's going to be my last part? Yeah. Yeah, I'm just going to write it as 6 times negative 1, just so I stick with the order v first, then w. V first, then w. So 6 times negative 1. All right, so we do that out. It gives us 10 minus 9 minus 6. What's 10 minus 9 minus 6? Negative what? 5. Yep, negative 5. Okay, so that is the dot product between two vectors in 3D. Now, what did we use the dot product to figure out? Yeah,
Plugged in a cosine to find the angle.
to find the angle. Yep, so that's the next thing. So now we're going to find the angle between two vectors in 3D. Okay, so to find the angle, I'll have to give you two vectors, like that. Each vector will have an x, a y, and a z component. And what was the formula in 2D to find the angle? Worse?
Cosine equals u times v over the magnitude of u and v.
So cosine of
Theta.
theta. equals the dot product over the product of the magnitudes. Well, in 3D, it's the same formula. The reason we can use the same formula is because the dot product in the top is now a 3D dot product. And we just looked at how to do that right here. The magnitudes in the bottom are 3D magnitudes. And we just looked at how to do that right here. So it's exactly the same formula we did yesterday. It's just a 3D dot product over two three-dimensional magnitudes. And the same trick works if you want to know if they're perpendicular. All you have to do is check if the dot product comes out to zero. We're just checking for 0. Yep. All right, so let's find the angle between these two vectors. So 2i minus 3j plus 6k, and 5i plus 3j minus k. Okay, so you can do them in any order you want. You got to find all three. I usually start with the dot product. Okay, how about Caleb? Can you give me the whole calculation I would do for the dot product?
Yeah. That's going to be
Yep.
5
2 times 5.
plus -3 times 3
-3 times 3. Yep.
plus 6 times -1.
6 times -1. Perfect, and we already did that. That's the exact dot product I gave you up above. 2 times 5, -3 times 3, 6 times -1. Dot product is -5. Okay, magnitude of u. Could someone else give me my calculation for that? Yeah.
Square root of 2 squared
2 squared,
plus -3 squared.
so that's -3 squared.
6 squared.
It's 36. And that's going to give me 13 plus 36. 13 plus 36 is 49. And square root of 49 gives me 7. Not always going to get a nice answer, but for that one we did. And how about magnitude of v? What am I going to do for that, Julia?
I squared, which is 25,
25
plus 3 squared, which is 9,
plus 9
plus 1,
plus 1.
which equals 36,
Square root of how much?
35.
35. Yep. And we can't simplify that, so we're done with the magnitude. And now we fill it all into the formula. Cosine theta equals the dot product over the product of the magnitudes. So dot product is -5. Product of the magnitudes is 7 root 35. Don't round the square root of 35 off. Just leave it as the square root of 35. We're going to type that into the calculator, and then it'll figure it all out. Remember, though, because the denominator has a product in it, you need to put the denominator in parentheses on the calculator. Okay, so type it in just like this. -5 divided by 7 root 35. So the angle between these two vectors is 96.93.
Do you want that in 2 decimal places?
Yeah, we'll generally go to 2. Yep. Okay, any question on that one? So now we've done everything that we did in 2D, we've done it in 3D. There's one last thing that we're going to do that we didn't do in 2D, because I told you you can't. Does anybody remember what I said yesterday that was? Yeah?
Was it dividing?
Nope, there's no division with vectors. There's really no such thing as division. But I think I mentioned it yesterday. No, not finding a missing letter. There's a name. It's another kind of product. Yeah?
Cross product?
Cross product. So dot product, that's what we did in 2D. We just reviewed it in 3D. Cross product, we haven't done. And you can't do cross product in 2D. There's no such thing. So cross product, first of all, it only applies to 3D. So the cross product is a second way to multiply 2 vectors. Okay, and first thing I want to do is show you the symbol. If you are being asked to do a cross product, this is how it would look. You'd have your 2 vectors written, and there'll be a little X, a little cross between them. Okay, and the way you pronounce that is V cross W. Just like we do dot product, V dot W, you say V cross W. So that's why we don't say multiply, because if you told me to multiply V and W, then my next question will be which way? Do you want a dot product or a cross product? And they're not the same. So I just said that. Cross product only applies to 3D vectors. Okay, as far as the applications, we don't get into the applications as much. To do the application, you know a little bit of physics. That's one area that we use cross products, or calculus. But we're just going to learn how to find a cross product, and then if you take a future class or if you do engineering or anything like that, you'll practice applications. Now, there's lots of different ways to do a cross product. Right? The way that I'm going to show you how to do it isn't necessarily the fastest, but it requires you to know the least amount of things to do. Okay? There is a faster way to do it, but we have to know some other things that we've never learned to do it the fast way. Having to do with matrices and what are called determinants. But that's not something we've ever studied. So we're going to look at what's called Sarris's rule, and that will help us to find it. All right, so I'm going to show you how to use Sarris's rule to find a cross product. This rule is basically going to involve you creating a table, and then you're going to look at the table, and that's going to help you figure out the answer. So when we do a cross product, the first thing is I will give you 2 vectors. When we do an actual problem, it'll be like that. You'll know all the numbers. For now, I'm not going to fill in any of the numbers. I'm just going to leave them generic. ABC, ABC. But you'll be given all 6 of those numbers. So the first thing that we want to do is we're going to take all that information and we're going to create a matrix out of it. A matrix just means it's a table with rows and columns. We're going to create a table that has 3 rows, 3 columns. It's going to look like that. On each one of those lines, you're going to write something down. Okay? And I'm going to show you what you write down. So across the top, you're going to write the letters I, J, K. Those stand for the bold vectors we talked about earlier in the week. IJK goes across the top. Then in the second row, you're going to write down the three things I underlined in yellow. A1, B1, C1. A1, B1, C1. Okay, and in the bottom row, you're going to write down the three numbers, A2, B2, C2. Okay. Any question on that first part? So again, what this rule really is it's kind of a visual trick that somehow it just gives you the right answer and you don't have to really understand what's going into it and why it works. Okay, so it's like a trick that gives you the right answer using this table. All right, and the last thing we have to do to our table is create a copy of the first two columns. So we're going to take these two columns and we're going to put a copy of them right next to it. So the top row, and I don't want you to worry about the things I have circled yet. We'll get to that. So now the top row is going to say IJK, and then you're going to copy the first two over again, IJ. Okay. Second row, A1, B1, C1. And then what are the next two going to be? A1, B1, yep. And the bottom row, A2, B2, C2. And what will the last two be? A2, B2. Yep. A2, B2. So that's what we need now to do this rule. Okay, everything is now set up. What we're going to do is we're going to look at diagonals, different diagonals, and we're going to multiply the diagonals together. I'm going to start with the diagonals that go down and to the right. To be a diagonal, it has to have three things in it. This is not a diagonal. And if I go like this, it only has two. So we're going to start with there's only three diagonals that go down and to the right. Here's the first one. Here's the second one. And here's the third one. Now what the important part of this is, you need to know that B1 and C2 and I are all on a diagonal. Without this chart, that'd be a lot to memorize. Then you'd have to know that the J, the C1, and the A2 are all on the same diagonal, and K, A1, B2. Okay, that's a lot to think about, but if you look at it in the table, you don't have to think about it. You just look at the diagonal after you set it up. And then we're going to look at the three other diagonals. These are the diagonals that go down and to the left. K, B1, and A2 are on a diagonal. I, C1, and B2. And J, A1, and C2. If you don't write them nicely, it doesn't look good. So try to make sure you put everything lined up nice. Right. So to make it simple how I refer to these, I'll call this blue diagonal 1, blue diagonal 2, blue diagonal 3. Red diagonal 1, red 2, red 3. Okay. Any question on those diagonals?
Take a picture of that.
Sure. Just make sure it's just a forward. Now, here's how you find the cross product. First thing you're going to do is you're going to multiply everything that's on red diagonal number 1 together. the I, the B1, and the C2. Then you're going to multiply everything that's on red diagonal number 2 together. The J, C1, and the A2. Then you're going to multiply everything that's on red diagonal number 3 together. That's the J, the C1, and the A2. Once you multiply those 3 things together, they all get added up. This plus this plus this. Okay. So those are the red. I think, did I change the color of this one on accident? Should be red. Those are all the red diagonals. Which diagonals haven't we used yet? The blue ones. Well, we're going to do the same thing, except we're going to subtract. You're going to subtract the product of K, B1, and A2. Then you're going to subtract the product of I, C1, and B2. And then you're going to subtract the product of J, A1, and C2. Okay, that's how you find the cross product. And again, we don't have to really know why. Why do you multiply A2 times B1? It's just, that's not for us to really understand right now. Just that's the pattern you follow when you do a cross product. And when the second 2 rows are all numbers, then it seems a lot easier. So I'll keep that up. And let's try this one. All right, so they want us to find the cross product, and those are the 2 vectors. Okay, let's start by putting let's do the first row. What are the 3 letters that we put across the top? Yeah. I-J-K. I-J-K. What are going to be the 3 numbers in the next row? Yeah.
A1, B1, C1.
Okay, but how about for this problem?
Oh. I and J. What was the question?
I'm looking to fill out the second row.
So it would be 2, 3, 5.
2, 3, 5. Okay, and the third row. Yeah. 1, 2, 3. All right. So we've got those 3 rows filled out. What do we have to do next so that we can start doing the diagonals? Yep.
We have to take rows I and J and then move them, copy them and move them over past row K.
Yep. So we're going to put a copy. This will be IJ. This will be 2, 3. And that'll be 1, 2. Okay, so now everything is set up. We're going to start by looking at all the diagonals that go down and to the right. I3, 3. That's the first one. Okay. Second one, J5, 1. Third one, K2, 2. Let's do those first. What's I times 3 times 3? Yep. 9i. What's J times 5 times 1? Yep. 5J. And K times 2 times 2. Yep. 4K. Okay, so I found those 3 and I added them all up. Plus, plus. Now, let's do the ones that go down and to the right. What's k times 3 times 1? 3k. And for these, you're going to do the opposite. Okay, so I'm going to subtract 3k. I'm going to subtract, what's I times 5 times 2? Yeah? 10 I, yep. And then I'm going to subtract j times 2 times 3. It's j times 2 times 3. Yep. 6j. Now, could these end up being a plus? They could. Like, if this was a negative 2 right here, that would be j times negative 2 times 3. That would be negative 6j. And when you subtract negative 6j, it does become a plus. Okay, so that can happen, but it didn't here. So let me get rid of that negative. Okay. All right. So now we just combine our like terms, and that's the cross product. What's 9i minus 10i? Negative I. What's 5j minus 6j? Negative j. And what's 4k minus 3k? K. And that is a vector, so that's the first thing about a cross product. The answer is a vector, and that is the cross product. Negative I minus j plus k. And that's V cross W. So the last one we're going to do is the same problem again. I just want to do W cross V. What's going to change in the setup? Still going to have IJK. That's not going to change. But what are going to be the numbers in the second row? Yep.
It'll be 3, 2, wait, no. It'll be 1, 2, 3, 1, 2.
I'm going to have a 1, 2, 3, because now W comes before V. 1, 2, 3. And what's going to be in the last row? 2, 3, 5. Okay. And what do we do with that?
Add the other 2 rows.
Yep. Put these 2 columns over here. IJ, 1, 2, 2, 3. And the question we want to see is, do we get the same answer? Okay. So this was V cross W. Okay, so let's start with down and to the right. I25. So I'm going to write it as 10I. How about J32? 6J. And K13? 3K. Minus K22. Minus 4K. I33. So minus 9I. And J15.
5J.
So subtract the 5J. Let's combine like terms and see what happens. What's 10I minus 9I? I. What's 6J? Take away 5J. J. And what's 3K minus 4K? Negative K. So, did we get the same answer? No. But is there a connection between the two? Yep.
They're opposites.
They're opposites. -1, -1, +1, +1, +1, -1. So once you find one cross product, you automatically know the other one. Just take all the numbers and make them the opposite. Yep. Okay. Once you know the steps to follow, it really doesn't take that long to do a cross product. It's just remembering which diagonals you add and which ones you subtract. And remember, any of these can switch signs if you have negative numbers in your table. Right? Like if this was a -5 right here, this would be j times 1 times -5, and you'd be subtracting -5j, which would make it addition. So this could switch to addition if you throw in a negative. Okay, but I didn't put any negative. Okay, and that's the cross product. Any question on that? All right. So the homework, mostly in the book, but there are 2 cross product problems, and those are written on the board. So do the questions on page 363 and find these 2 cross products. Really, it's just one cross product because once you get one, you automatically know the other. While you guys are at lunch, I will pause the video and I will put the list of topics that are going to be on the test on the board. Okay, but I'm not going to be able to do that before you leave.